So now we will dive into some actual details. So hopefully now everything should be understandable. If it's not, ask questions. Fair warning is that the setup that we are using is not the setup I'm used to working with. In particular, my handwriting, which is not great, is even worse here. So please, please, if something is illegible, just let me know. And somehow it's a little bit awkward because when I write, yeah, we will figure it out. But yeah, sorry if this is not perfect. Okay, so what we will talk about? We will talk about like how do you actually do continuous optimization in the real world. Okay, and essentially continuous optimization in a sense has only one problem it tries to solve, and it's called unconstrained minimization, in which we just have some function f and just want to find this minimum. Okay, that's the whole problem. Very simple, but of course very powerful. So for now, by the way, the details is exactly hidden in trying to understand what the function f actually is. Okay, so first of all, we always will assume it's continuous, so that we don't run into some like strange problems from analysis. And for now, we'll also assume that it's differentiable. Okay, so essentially you can actually take derivatives and of higher order derivatives, partial derivatives of at every point. So in particular, notice that this problem is like very powerful because like if you want to do maximization, you can just think of minimizing minus your function, right? Then also if you wanted to actually have some constraints, so you would like x to just belong to some particular set S, what you do, you just take the original function and some the proxy function, which is let's say 0 if this point belongs to S, and it's like plus infinity to the point that it doesn't belong. So it will just like repel you away from from points that are not in S. Of course, this function now is not differentiable, but let's not worry about this, okay, for now. Okay, but the point is that you can actually, even though this is a very simple problem, it can express almost everything that you want to do in continuous optimization. So, okay. So, so now the question is, this is the problem, how we solve it. Okay. Oh, sorry. Wow. Okay, and we already know what is the approach. Okay, so we want to use this kind of iterative method that somehow starts with some solution and then repeatedly is getting better and better answer, like refines its answer in a greedy way. Okay, so essentially, okay, so how would we would like to do that? So imagine. Okay, so what we want to get is just like we want to get a sequence of points. So I will put these numbers at the top to denote like which iteration this solution corresponds to. So at the beginning we have like x0. So they're not powers, these are just like iterations. So then we want to get from this x1. Then from this we want to get x2 and so on. And somehow what we would always like to do, we would like to make sure we are always making improvement. So essentially that for every iteration t, if I look at the value of my function at the point t plus 1, it should be strictly smaller than the value of the previous function. So at least we always want to make progress. We are not quantifying yet how much progress we make, but at least we want to make progress. Okay. So now so now there is a question, right? So imagine that's not working how it's supposed to. Okay. So imagine I have my point xt. Okay, and I would like to figure out what the next point should be that improves the value of the function here. Okay, and this is now the crucial and the only principle of continuous optimization. It just says, okay, so essentially what we do is that like we are trying to understand the function not globally, so we don't try to find analytic solution to it. We just try to understand it locally. And when we think about functions locally, then there is like a great, very nice way of approximating any function in the neighborhood of a given point that we know as Taylor approximation. Okay, so there is Taylor approximation. Okay, what it tells us is that if I want to understand how the function looks like at some point x, which is like xt plus some delta, some displacement delta, which will be my step, then essentially I can express it as the value of the function of y is the value at the current point. Okay. Sorry, it should be t. Okay, plus, then there is first order term, so there is like a gradient of the function. So by the way, the function f is its argument is some just vector, m-dimensional vector, and it returns a single real value. Okay, so now we essentially, it's the gradient at this point, okay, times sorry, times delta plus the second order term, which is delta transpose the Hessian at this point times delta plus higher and higher order term. So I know that if I take this infinite series, it will exactly give me the value. It give me the value at the at the point fy, no matter how far y is. Okay, but this only works if I take all the infinite number of terms in the series. And now the whole idea of gradient descent is like, since we only care about making local improvement, then essentially we can just truncate this Taylor approximation to just like end up with something very simple. So specifically, we do the simplest thing possible. So essentially, what we think about our function, we just look at its sort of linear approximation. Sorry. Linear approximation, well, f of y, which is just exactly this term. It's just exactly, I just look at the constant term plus just the correction to the value that comes from the first order approximation. Okay, so in particular, so what I want to do is that I just want to think that my function is actually exactly this linear function, and now I want to figure out, okay, in what direction should I move to minimize this linear approximation the most? Okay, so essentially, best move to minimize f hat is essentially what I should do. My new point should be my old point, because of course I'm moving from that point in the direction of, well, essentially, if you analyze this thing and you ask yourself, okay, what is the direction that it minimizes the most? Of course, you want to go in the direction of minus gradient, okay? Because the only thing that depends on where we go is this delta. So you just wanted to have like maximum inner product, so it has to be essentially collinear with the gradient, and then you want to go in the opposite direction because you want to minimize the function, okay? So then essentially there will be some scaling factor times the gradient at the point.
How much you care about efforts there?
Sorry?
How much you care about efforts? Because you're losing a lot of things, right?
So, about what, eta? Or?
Yeah, the difference between Fy and the value that.
Well, that's where the devil is in details. That's exactly that. We care about it a lot. Because if this approximation was exact, then I could finish my minimization in one step, right? So exactly that's why we have the step size eta here. Because now it's exactly this key interplay. So the whole principle of continuous optimization is that every function, no matter how complicated, it is simple if you look at the neighborhood of the sufficiently small neighborhood of this point. So now what we want to do is just want to figure out, how large can we clearly we want to make as much progress as possible. So we want eta to be large, but on the other hand, we want our linear approximation to make sense. So essentially, we would like the linear approximation to not be overcome. So whatever gain we get on the linear approximation, not will be overcome by the terms coming from the other terms. So essentially, somehow, so the idea here is that if I look at this tail, then it roughly scales as delta squared. Okay. While on the other hand, here the improvement is proportional to the delta. So this really should give you intuition that if delta is sufficiently small, I can always make sure that whatever progress I get from here, it dwarfs the progress, the dwarfs any kind of error that comes from thinking of this function as linear as opposed to whatever this function really is. Okay? And that's really this is the key principle of the whole continuous optimization, just saying that if you look close enough, if delta is small enough, then you are guaranteed that even though you think of your function as a linear function and you minimize this directly, it actually ends up minimizing the arbitrary function, no matter how complicated it is in general. Okay, and the whole idea of continuous optimization is just exactly as how big the delta can be. So you make, because the bigger the delta, the more progress you can make. Okay, so let's try to understand that. So somehow, by the way, there is just one picture, is that, like, imagine our function is, something complicated, and we are maybe here. Okay, maybe this is more interesting. Here is our point xt. So what we are really doing is that we look at this like local best linear approximation of our function, which is just like I look at the tangent line. Okay, that is exactly like touching my function at this point, and this is my linear approximation. That's exactly what I get from the linear term. So this is the, the f tilde, and essentially, like if I'm close enough, this approximation is actually pretty good, but then it degrades as you go far. But we just like want to hope, we want to make displacement small enough. So we want the x t plus 1 to be small enough, so actually we still, whatever the linear predictor tells us, is still actually a decent improvement point. Okay, so this is the principle, but now we have to put some numbers on that. So for that, we actually have to quantify how nice the function is from the point of view of this local approximation. Yes, because if it's like varying crazily, then clearly, like if it was discontinuous, then of course this would not work. But then also, especially you need something like some nice way that this function cannot change too crazily, too fast, and you want to quantify that. Okay, and the notion that when you try to when you want to quantify that, the notion you arrive to is one convenient notion to do it is notion of beta smoothness. So clearly, like the function has to be smooth to even this approximation make sense. But we actually want to quantify it, and what it means is that essentially the function is beta smooth if for any 2 points, if I look at the value, if I look at the gradient of the function at point x and at points y, then it should not be much different than beta times the distance between these 2 points. Okay? So I'm just saying this sort of says that this local approximation, the slope of this local approximation should not vary too crazily. Like it essentially should be continuous in some way. Okay? And actually equivalently, so this is equivalent to just saying, so if the function is twice differentiable, it's equivalent to saying that essentially for any, maybe let's call it delta, sorry. For any delta and any point x, what happens is if I look at the Hessian at x and I look at this quadratic form, okay, then it never, it's always at most beta times the norm of the displacement squared. So again, this just tells you that this essentially, well, equivalently just says that the largest eigenvalue of the Hessian is at most beta. Okay? So do we understand the notion? Like again, it might not be clear yet why this is the notion we care about, but like, are we comfortable? In particular, do we know what Hessian is and what gradient is? Not everyone does. I didn't before doing this. So, okay. Okay, I think I will define it anyway because somehow the look on the faces seems that it's not clear. So what is the gradient of the function? It's just a vector, okay, in which it has coordinate per every input variable, and this value is just the partial derivative of the function at x with respect to this, to this coordinate. So this is like here you have like the derivative with respect to the first coordinate. Here we have with respect to the second coordinate, and so on. So this is just a vector. So it just tells you like if I vary this particular coordinate, how function will change locally. And then the Hessian is just a matrix. It's like m by m matrix, which has the second order derivatives here. So essentially is on the diagonal it has just this like I just take this same variable twice. Okay, but yeah, in general, okay, maybe that's a better way to view it. Is just if I look at the ij entry of the Hessian, it's exactly the second partial derivative of f with respect to xi and xj. Okay? Good. So now, why is the smoothness interesting? Well, essentially, we all know that there is another version of the Taylor approximation that actually allows us to get exact, like essentially just have a finite sum version of it. So this is Taylor approximation second version. What it says is that essentially my value at y will be, so if delta plus x is equal to y, then my value of y will be fx plus the gradient term, but then plus essentially I will call it delta hat. By the way, there is 1/2 here. Delta hat fx delta hat for certain. Sorry, no. It's 1/2. This is the same delta. The only thing that changes is that there is this. We look at the Hessian at some point z. Okay, where z is something that is on a line between x and y. Okay, I mean it's of course in higher dimension, but essentially I look at the line between x and y, and there is just some point in between where if I take Hessian at that point, it will be exact. Like essentially, this will be exactly this will be exactly the correct exact approximation. And now what smoothness gives me something very dramatic is happening there. I'm happy that it's so inspiring what I'm doing here. So essentially, what it tells us is that essentially it means that f and y, since I know that for any point in my domain, the largest eigenvalue, like this is at most beta times the norm squared of delta. That was recall. That was one way to see. That was one way to see what the beta smoothness means. Then it means it holds for any point, not only for x. So I can just change it like that, and I get that essentially I always can upper bound the function, the function at y by fx plus fx delta plus 1/2 beta times delta squared. Okay, so this is the condition I get about about this function thanks to beta smoothness, and it actually has a very nice intuitive meaning graphically. So essentially, imagine that again, I have my function, okay, and then I look at some point. So this is my x, and then I look at my linear approximation. Okay. Now what it tells me is that linear approximation degrades very quickly as I move, and it can either undershoot or overshoot as we go. But what smoothness tells me that if I now put a quadratic function, essentially that starts at this x, and there is a slope, and then there is this quadratic function that goes at the rate of beta, then I know that the whole function f everywhere is below this, is below this line. So essentially, if I define, if I define this as some kind of f hat, okay, this is my sort of like second order approximation of the function. The two conditions I have is that, at x, these two things coincide, they have the same value. But then for any y, I don't have equality, but at least I know that always this is upper bounding my function, no matter what is y there. Okay? So far so good, but that's essentially all that we need to now analyze. Yes?
If you have an oracle, you don't need to have a beta that holds for all pairs of points, right? You might have beta depending on x and y, or not.
Well, you could, yes. Well, except, you know, you need it local, like somehow you need it actually to be uniform everywhere. Like that's usually the way. Actually, you run into trouble when you say, because notice that here, you know, here I use the fact that for the z, it also will be beta smooth, right? But then z is a function of y. So essentially, if y is going farther, then essentially also z is going farther. So I actually need the same beta to be true for larger neighborhood. Again, in the end, we still use it somewhat locally, so that will be fine. But then things become unpleasant when you analyze them. But yes, so I want you to think about it just that it has to be uniform. You know, in real world, you can actually do something more, but like the idea is better. You know, it's better to keep in mind for now that it's just the same everywhere.
How expensive it is to compute z, or if you estimate?
Well, you never need to compute z. So essentially, like usually you get it from intermediate value theorem. So it's not, but like you don't need to know. Like as long as like it's possible to analytically analyze what is the worst case beta, and then you don't need to solve it. Actually, you never really even need to know beta. It will tell you how fast you converge, but to run the algorithm, as you will see, it's actually you don't even need to know beta. It will tell you how fast it just governs your speed, but you don't have to know it. Okay, so let's now analyze, how much progress does a gradient descent step make? So remember that we had some point xt, and now we move to a point. So t plus 1, which was xt minus eta delta f of t, right? So now how much progress, like what can we say about the value of the function, of the true value of the function at the point t plus 1? Well, we know that is at most f hat of xt plus 1, right? This is what we get from this majorization statement. Okay, but now what is it? Well, the nice thing is that we know explicitly what f hat is, so we can just plug things in. So this is equal to the f at x plus t, like xt, okay, plus the gradient fx transpose. Okay, and then I will just minus eta times, well, the gradient of x, okay, plus d eta squared. Am I doing it right? Just is it good? Sorry. Oh yeah, of course it's good. Yes, beta, and here I again have this term like the gradient times the gradient. Okay, so this is what I get. This is exact, like this is equality here, like this is equality here. So now, well, what is this? Well, this is just the norm of the gradient, right, squared. And the same goes for this. Okay, so what can I write? Well, I can write that this is, f of x t. Now it's like minus, I will just write these things as a common denominator, okay, of 1 minus eta times beta. Okay? So now it should be clear what is the setting of eta that we want to do, because clearly as eta grows, like this thing becomes negative, and essentially we are losing our progress. If eta is 0, we also are not making any progress because this eta will eat it up, right? So this is just a quadratic that essentially we are trying to maximize a negative quadratic. So essentially the best setting of eta is to set eta to be, I guess, just to make sure, yes, 1 over 2 beta. Okay? When I just set it like that, what I will get, that this is f the x, xt minus essentially, well, if I think I did the math right, so I will just write it. Okay, I think that's the that's the gain you are getting. Did I do the math right, or didn't I? Sorry, yes, I did it wrong, of course. Oh, if you plug it in, that's what you will get. Okay, so you see that actually you are, since the norm of the gradient is positive, you are making progress always. So you probably know that this is strictly smaller than f of xt, and the progress is proportional to the norm of the gradient, and inversely proportional to the smoothness.
But then it will be 0.
Sorry?
When you plug in eta equal to 1 over beta.
Yeah, then probably you see, I forgot that there is 2 here, because in the Taylor's approximation, it's in Taylor's approximation we have 1/2 here, which I forgot to. So I knew what I had to get, but then I cheated, and that's what is the problem. Thanks for catching it. And even though this setting seems to suggest you have to know beta, if you actually get it within, like, essentially what you really do in practice is that you just find, like, you just do binary search for what is the best eta that gives you the most improvement. So this just shows that there is a setting of eta that gives you at least that much improvement. So clearly whatever you will find will be at least that much. So you don't have to know beta explicitly. You just need to know that some beta exists. Okay? So that that tells you that that we are making the progress. Now, of course, it's hard to say what does progress really mean, because it's hard to say what is the norm of the gradient. Okay? So in particular, one thing that we should start talking about now is, saying, well, clearly we are not making progress, stop making progress whenever we reach a critical point, meaning when we have that x, the norm of the gradient, is close to 0. Okay, clearly we are not making much progress anymore, because our progress is proportional to the norm of the gradient. But what does it mean? So if actually I am at the point when the norm of the gradient is essentially close to 0 or just 0, what does it tell me about where I am in terms of the function? Does anyone know? Yes. So we are okay. There are three possibilities. So we can be either at local maximum, and this can only happen if you actually start the local maximum, but it can happen. Or we can be at local minimum, which is actually great, because we find some notion of minimality. But what is actually worse is the saddle point. Okay, so there is a point where indeed the gradient vanishes, but it's neither a local maximum or a local minimum. Okay, so this only can happen if you have at least 2 dimensions. In 1 dimension it doesn't happen. So let me just draw the picture in 1 dimension so things are easy. So yeah, so if you have our function, over here it would be a local maximum. Actually, if we just had exactly the local maximum, we would not move anywhere. We would just be confused. Similarly, these are the places that we could have ended, and of course here you would go forever down. But these are local minimas. And then there is this third situation when you have a saddle point. Okay, and this should be actually quite, making us quite unhappy, because it means that actually you never know, even if you end up at local minima, you never know what is the quality of the local minima that you can hear. So here maybe all the local minima seem to be pretty good, but imagine a situation where your function looks like that, right? And if you end up in this local minima, you might be very unhappy with yourself. Okay, so what can you do about this? Well, in general, you cannot do anything. So essentially, gradient descent is a method that, the nice thing is that actually it works for any function. But in general, it only gives you this kind of local minima kind of statement. So essentially, everything depends on what is the initial point you start your gradient descent from. So if I started from somewhere here, I would end up in this very good minimum. If I ended somewhere here, I would end up in bad minimum. And that's a whole science and also a lot of practice, how to figure out for specific functions what is the good point of start. So in particular, some of you have heard about deep learning, which corresponds to essentially the way you do it is, you actually are the way you train this models is by solving unconstrained minimization of some very complicated function, and then somehow you have to hope that the local minimas you end up with are good local minimas, which seems to be empirically happening, but no one can prove it. So why this is the case? But so this is the kind of regime which it's a gradient descent is a very useful paradigm, but it not always can guarantee you like getting good results. And and in theory we don't like this. Yes, like we like to know that in the end we get optimal answer in some sense. So sorry, this is not what happens. But fortunately it's not as bad, because there is actually some property of the function that actually would enable us to make sure that gradient descent always behaves in this robust way, and this notion is just convexity. Okay, so we say that f is convex if and only if what happens is that for any 2 points x and y and any lambda between 1 and 0, what I have is that if I look at the convex combination of the value of the function at this endpoint, so I look at fx plus 1 minus lambda fy, then what I would like to have is that this is always upper bounding the value of the function at the actual convex combination of these points. Okay, so pictorially, what I want to have is that, well, if this is y and this is x, then essentially, like the line that I get by just interpolating between the endpoint values is always upper bounding the line I get by actually exploring the function between these points. Okay, and this should hold for any x and y. So in particular, this function over here is not convex, because yes, it satisfies this condition over here, but it doesn't satisfy this condition for these 2 points, because here the function actually is above this thing. So essentially, like this at least identifies that this is a bad function for us from the point of view of convexity. And then what you can show, and this is like very easy exercise, that if f is convex, then essentially every critical point, so okay, then essentially if the norm of the gradient is 0 at some point, it implies that x is actually not only local minimum, but actually is a global minimum. Okay, so in particular, you cannot have situations like here, that when you have some local minima, that even if you end up in local minima, it may be suboptimal. Now, essentially, what happens is that like every local minimum is a global maximum as well. Okay, and somehow, so when you have convexity, you are very happy as a theorist, because now it's always the case that you will converge eventually to the global minimum of the solution. Okay, and it turns out that like the realm of convex function is very rich. Actually, a lot of problems that we know are convex. In particular, linear programming corresponds to minimizing a convex function. Max flow, as you will see, also corresponds to convex function. So actually, this is a very useful regime in which you can get provably optimal solutions eventually. But then it's important to keep in mind that there are some very important regimes like deep learning, where these things are totally not convex, but we still want to do something there, and that's the tragedy of theory, that we are not able yet to show any reason there what's going on. Okay.
Does it help to massage the function somehow so that you get the convex function solved and then?
Well, yes. So for instance, like EM algorithm, which is used in machine learning for a problem called maximum likelihood finding, which is a very non-convex problem. The way it works is that it always locally, for every point it is at, it defines local convexification of the function and minimizes that. And honestly, this is how gradient descent as well works. It's sort of like it thinks of this quadratic approximation locally and just tries to minimize that and hopes that things are good. So you can, but in the end, if function is non-convex, there is no escape against it, because in particular, you can phrase, again, the unconstrained minimization is a powerful primitive. You can phrase trisat or some NP-hard problems as a question of minimization, then exactly like finding the global minima is what it makes it difficult. So if you had this kind of method which always converges, you wouldn't have it. So this is actually like, it's a real thing. It's not a matter of just choosing different formulation. The non-convexity of a problem is actually a real thing. So in particular, like relaxation of like we have the whole business of LP relaxations of NP hat problems. So essentially, you can view them as a way of convexifying the function, but then there is something you have to pay because you will just like lose some quality. Like that's where the approximation factor comes in. Okay, but that's a great question. Okay. So okay, and one particular implication of convexity. Is that essentially we can refer it nicely to our Hessians. So what it says is that for any point y, what I have is that if I look at this quadratic form, then it's always non-negative. So essentially the Hessian is always a semi-definite matrix. Okay, and that actually will be quite useful. Because if we look back to our function f hat, then so far it was giving us only an upper bound estimate. But also what you can prove is that this means that for any y and any x, where delta as always is when delta is y is equal x plus delta, what happens is that f of y is always lower bounded by f of x plus the first order term. Okay, and the reason for this is that of course we have this other term here as well, 1/2, but since we know that for convex functions is always non-negative, I can just drop it and essentially just get with this relationship. So what it says is that if I have a convex function and I have a point x, then this first order approximation actually ends up being exactly like a lower bound globally for the function. Okay? Good. So now we at least know that there is a unique minimum to converge to. So now we can say something about how fast we converge. And so actually, well, the best way to do the convergence is by you need one more property. So far we had smoothness to say that I would just ask you okay. So what's the question?
Is it supposed to be 2 on this Hessian?
No, it's z. So it's again this point z that is like some point between.
But before you use like second exponent.
No. It's so before I. This is one good feature compared. There is proof for everything. Yeah. So here, it's no. So there is 2 in here, which denotes the Hessian, but this is z. This is just a point.
Yeah. So you like 2, but later on you want.
Okay. So maybe I made a mistake somewhere, but definitely. Oh yeah, there should be 2 here as well. But this is just how we denote the Hessian. That there is a 2. There's actually a reason for that, but let's not go into that. Okay. So now we would like to understand how quickly we converge, and actually it's easiest to think about the convergence when we sort of get a bit like convexity is already enough to get the convergence, but actually it will be more useful to have one more important property. So like the moment we have convexity and smoothness, we know that we will eventually converge to a global minimum. But if you want to analyze how fast, the other definition is called strong convexity, alpha strong convexity. And what it really says is essentially that for any y, if I look at this again, this quadratic, I look at this quadratic, the Hessian, the quadratic form of the Hessian. Sorry, it's y delta. Then it's actually not only so far convexity just gave us that this thing is non-negative, but actually here we just strengthen it and we say that it's actually at least alpha times the norm of the delta. So essentially, we are like making this definition of of convexity even stronger. So what you get out of that by the completely analogous derivation that we did for beta smoothness is that now I know that for any point x and y, what I have is that essentially I can lower bound my function by a quadratic. So let me just write it down and I will explain. Okay, it's no, sorry, it was good, sorry. Okay, so essentially what it means graphically is that now I have my function, okay, and I have some point x. So again, I look at the linear approximation, okay, and now from smoothness I knew that there is this quadratic that is always upper bounding my function. But now from strong convexity, I know that there is also a quadratic. Okay, so sorry, like let's make this picture a bit more clear. So let me just think of a function that looks like here. Okay, that's not a function. As you see, it's hard to write a properly strongly convex function. Okay, let's do something like this. So if I'm here, then again I have the linear approximation. Then the smoothness gives me the one quadratic that somehow upper bounds everything. But now the strong convexity tells me that there is a lower bounding quadratic that essentially lower bounds my function everywhere. Okay, and somehow the intuition is, if I could use different colors, I guess I can. So the intuition, this is actually important, so let me rewrite it. The intuition is, so let's say I have my function like that. Okay, this is x. Now, essentially this is my approximation. This is the upper bounding parabol, and now this will be the lower bounding. Oh, sorry. This will be the lower bounding parabol. So essentially, the way it actually helps me is that it gives me a lower bound. Essentially, like how far can the optimal point be? Because essentially, if this parabol is lower bounding my function everywhere, and you know that eventually it goes to infinity on both sides, it means that my optimum, like so, yeah, eventually this overcomes and goes to infinity. So essentially, I know that my optimum has to lie somewhere here. It cannot just be extremely far away that I will never converge. Somehow I have now a control over how close my actual minimum, which is over here this time, this is the x star, is from me. Okay, and this actually allows me to talk specifically about convergence. Okay, so now this is the sort of the intuition that somehow by approximating your function from upper bound by quadratic and from lower bound by quadratic, you can start reasoning about how far you are from optimum. And now the way the math works is just the following. So now finally we can get some convergence analysis. So essentially what we have is that, okay, so what we will do is that let x star be the minimizer of the function. Okay, so this is the point that we would like to converge to. Okay, now what I will do, I will measure how far I am from this point in L2 norm, and I will analyze how much I improve this distance in each iteration. Okay, so essentially, so this will be my potential, and I will show that each step of my method reduces potential by some significant amount. Okay, so let's just try to do that. So essentially, after I execute one step of my and this is squared of my method, what will I get? Well, this is by definition xt minus eta, the gradient at xt minus x star. Okay, I just use definition of the algorithm. So this is equal to well, this is equal to what? It is equal to essentially, well, you know this this equality, right? That x minus y is equal to the norm of x squared plus norm of y squared minus 2 like x times y. So this is well, this is the usual L2 norm inequality. So what you get if you apply it to this and this, sorry, to these two terms and then to this term separately, what you will get is that xt minus x star squared plus, you know, lambda dfxt squared, and then there is minus 2 eta df x star transpose x t minus x star. Okay, so this is what we get. Now, nice thing is this is just the potential that we just had before, right? This is just the potential we had in the previous step. So we just need to analyze. We just need to analyze this part. Okay, and what we will get is that, well, this improvement, so the improvement of the potential is exactly, well, okay, so so essentially it's 2 eta delta f xt minus x star minus the norm of the gradient squared. Okay, and now all that we have to do, we just have to reason about, you know, how big this is. And you know, since I'm running a little bit behind, let me just skip. Actually, there's just a couple of lines. But so what you will get out of this is that essentially your potential, like how far you are from where you started after the step, it will be roughly 1 minus alpha over beta times xt minus x star. I will just put out the note with all the derivation here, because yeah, the point is that essentially what happens is that in each iteration we are reducing this initial distance. So essentially, you know, if we like unroll it back, this will be at most 1 minus alpha beta to the t of the initial distance to the optimum. Okay, so we see that, you know, there's a geometric decrease of this distance each time, you know, each time we take a step. So essentially, if I define this quantity to be kappa, then after roughly sorry, this will be kappa to minus 1. So it will be kappa times log the initial distance to the optimum over epsilon. I will essentially have a guarantee that my point is, well, at most within epsilon of the optimal one. Okay, so essentially it just tells me that my rate of convergence of the algorithm is really dependent on this kappa, which again is just beta over alpha, and this quantity actually has its name, it's condition number. And it essentially tells me, you know, this is the ratio of, like, so always beta is always larger than alpha, so this is always greater or equal to 1. And this number just tells me, like, locally, how well can I approximate from below and above my function by a quadratic. Okay? So in particular, if the function was just a quadratic, this would be 1, and you would have a very quick convergence. If it's very wiggly, then these things actually have to be taken to be very big. So like, well, alpha has to be very small and beta has to be large. So this thing is large, and then the convergence is much slower. Okay, but somehow in the end, you will get this kind of convergence. Okay, and this is really essentially the only convergence proof, even though I didn't finish it. The only convergence proof that you have to know to do most of the continuous optimization, because essentially much of the continuous optimization is trying to figure out what alpha and beta is and choosing the functions that have this alpha and beta pretty good for your problem. So now, okay, so let's just try to apply it to max flow to just see how this kind of machinery plays out. And as you will see, we will run into a couple of problems when we try to do that. So,
how much time takes this optimization?
Sorry?
How much time takes this optimization?
Well, this optimization is essentially computing of the gradient, right? So usually it depends on your function, but usually these gradients are something simple to do. Usually you can do it in linear time. So essentially you just need the computing of the gradient of the function. Like say for L2 norm, this is very simple. And then you just need to apply the update, right? So it's a.
When you compute Hessian, you have like n square, right? And
sorry?
When you compute delta n square on Hessian.
No, you never compute the Hessian. So that's the point. The algorithm just updates. By the gradient. When you analyze it, you look at the Hessian. But it's only for analysis, not for the algorithm. So if you had to compute Hessian every step, that would be hopeless. Okay. So let's apply it to max flow. So recall that I told you like how to translate max flow into linear algebraic terms. So this is like minimize L infinity norm. Okay, so maybe f is not the right, it's not the best. Let's call it x now, right? Because f was a flow, but here f is a function that we are minimizing. So it's minimizing over x, but like not over all the x. It's not an unconstrained minimization. What it actually is I want this x to belong to fst, where fst is just the set, like the space of all the st flows. Right? Now remember that when we talked about electrical flows, we actually already derived a way of checking for a vector if it's an st flow. It just corresponds to the condition that the vector x has to be such that if I apply this matrix X to it, then I will get this vector ST that has like 0, zeros and only -1 at S and 1 at T. That was the condition. So this essentially tells us that the space of X's, so the space of unit ST flows, is exactly an affine subspace. Okay? But I still actually, I'm not, so if I cannot yet apply what I just told you about to this problem, because first of all, there is a constraint. So I have to take care of it somehow. So let's just deal with this. And the other thing will be that actually this thing is not differentiable everywhere. Right? Because this thing, like in one dimension, this is just absolute value. So as you know, absolute value has this one point here. That actually when it's not differentiable, and even though this is only one point, it's actually a big deal, and I will talk about it later.
It can be very simple. Just can you please explain? So why it's equivalent? So the minimum, once again,
So essentially, okay, it's unit capacity, right? So unit capacity, like if I asking yourself, okay, how much flow can you push from S to T subject to never have any flow be more than 1? You can equivalently think, how much flow do I have to push? I want to push 1 unit of flow, but then I want to use up as little of maximum, like I want the maximum flow to be as small as possible. So essentially by multiplying by whatever is, f star, you just go between one and the other formulation. In particular, the optimum for one is just a scaled optimum for the other. Right? It's okay, I can talk more about this offline, but this is just really completely equivalent. It's just like, question is if you think of keeping capacities constant and increasing the value of the flow, or keeping the value constant and then decreasing the capacities. Okay, so now, so the first thing, constraints. Well, we already know from the previous lecture to know what to do with constraints. You essentially add this projection step. Okay, so essentially if you have your set and then you like do this step according to the update of the gradient, then what you do then in the end you end up finding the point that is the closest in the feasible space, and that's your new point. Of course, the question here will be, how does adding this projection step plays out with the convergence analysis that we just did? And the nice thing is that actually it completely works very nicely, because our convergence analysis was all that it was talking about was not about the values, it was talking about how close we are to the optimum. Okay, so somewhere here is x star that we want to converge to, and essentially the only thing we were measuring was the distance between like xt, and here we have xt plus 1. And what you can see is that essentially we proved already that if I measured my new distance between this point and this point, then this distance would decrease. By the way, the picture is lying to us, so let's change it. So essentially we have feasible space, we have xt, and then we take a gradient step. This is xt plus 1, and the optimum is somewhere here. So we know already that if I compare this distance to this distance, then this distance is larger than this distance over here. But now I'm taking a projection, so now I'm moving somewhere here. How could it affect the distance, like doing the projection? Well, what is like the Pythagoras identity tells us that essentially if I measure the distance between this point and this point, and then I project this point on this space, provided that this point already was in this space, then I can only bring two things closer. Such projections are only contractive in the distance. So essentially I only can actually make even more progress by adding the projection. Okay, so this says that just adding projection step, everything works as it did, so I don't have to do any extra work. Essentially, just because the nature of the proof I had, I didn't have to do any work. It just works. So now the other thing that happens is that actually, yes.
So is it right it's happening because FST is a thing of space?
Is affine space? Yeah. Well, no. It works for any convex subspace. So as long as this subspace, as long as this is convex, which is affine is just one of the examples, then this will work. Okay. So now the second problem is that this function, if I look at this function f of x is equal to L infinity, which is the function I'm minimizing, there's a couple of problems of them. First of all, it's not differentiable. And second of all, it's not alpha strongly convex. Okay, so well, how do we deal with it? So I just tell you. So there are like two ways to deal with it. So there is actually, first of all, instead of gradients, use subgradients. So that's the reason why in the slides we have subgradients. Essentially, so what is the problem? So since the function, this function f is still convex, then essentially the only way we might not have a gradient is because things are not unique. So essentially the situation I have here, right, is that if I'm here, the gradient is well defined, it's unique. But if I'm here, there's actually many gradients. So essentially there's many ways for me to write a line that will be lower bounding my function. This could be one, this could be one, there can be many of them. And essentially all we are saying is that that's fine. You just so any of this line is a subgradient. So the subgradient is not uniquely defined. It's just like a set. So anything so essentially subgradient. Oh, okay, I will not write it. I will just say it in words. Essentially, any of these lines is nice. We will just take whatever line we get. Okay, so it doesn't have to be used unique. So the differentiability is not a priori a problem. But then the problem is, and there is some analysis that you can do that I will not do. Analysis that proves much weaker convergence. Okay, but actually a better way to deal with this problem. This is actually very something very nice. Is to do something called smoothing. So essentially what you do is that even though of your original function is not nice, it's not smooth, or it's not even differentiable, still what you will do, you will introduce a proxy function that is much nicer, but is much smoother. So sort of like in terms of convexity, the convexification usually might lose you a lot. Like there is no good way of convexifying arbitrary functions. With smoothing, actually you can gain quite a lot. There's a canonical way of doing it that actually you don't really pay much for using it. But I will not talk about the whole theory of smoothing. By the way, Yuri Nesterov is a king of this domain. So he's a Russian mathematician who, well, now is in the US, but no, actually now is in Belgium. But yeah, he's essentially like absolutely towering figure in this field. So he has a whole theory how to do it. But if I just think about L infinity norm, okay, then essentially the convenient way to smoothen this is to use something called softmax function, which is just defined as a logarithm, natural logarithm of sum over all the coordinates of e2 xi over delta plus e2 minus xi over delta over 2m. Okay, so what does it mean? Well, essentially, yeah, this is a function. It evaluates to something. Okay, so essentially, notice the following thing. So first of all, what happens is that, just let me make sure. So first of all, one observation to make is that S max of delta x is always upper bounded by L infinity norm. Okay, so essentially, like this, I will leave this as an exercise, but this is not hard to see. And from the other direction, what you can show is that S max of delta x is always at least the L infinity norm minus delta times log of 2m. Okay, so essentially, like modulo this additive factor that depends on delta, it essentially is very nicely tracing the L infinity norm. So sort of the picture is, so in one dimension, if this is my absolute value function, then the way this works is like it's something that looks like this. Okay, so essentially it's like smoothing this kind of this sharp edge over here and just making it much nicer. Okay, and essentially, so this is so essentially you see that you expect this function to be smooth, and you indeed can show that S max of delta is is beta smooth with beta being roughly 1 over delta. Okay, so we have this very nice trade-off here that on one hand we want delta to be as small as possible because that's the quality of our approximation. Like essentially, the bigger the delta, the less honest approximation of L infinity we are. On the other hand, the smaller the delta, the larger our smoothness is. And again, you expect it inherently to be so, right? Because in the end, in the limit, it's something that is very non-smooth. So just to be able to smoothen out this sharp edge, you have to pay something. You have to move away from the function a little bit. Okay, and essentially now. This is smoothing. There's actually a third problem. So even now things are smooth now. They are not alpha strongly convex. So this is a convex function, but not alpha strongly convex. Still, when you do the analysis, and I don't have, it's not much, but I should be wrapping up. Still, like even for when things are not where they are not strongly convex, what you can get you can show that you can get a point that is within epsilon of the value of the function after t is at least omega of beta times the initial distance to the point over epsilon. Okay, so this is a convergence analysis even if I don't have strong convexity. Notice that now I depend polynomially on epsilon. In previously I depended logarithmically on epsilon. So this is like exponentially worse. So that's actually bad. But this is actually inherent in max flow. But essentially, this already allows us to get our first non-trivial max flow algorithm using continuous optimization, because now we just have to plug in the numbers and get what we get. So essentially, so what is beta for max flow? For max flow, beta is, you know, as we just said, is the smoothness of the, so it's just like, it's 1 over epsilon, because like our target approximation will be epsilon, so we just take delta to be roughly epsilon. Okay, so this is the smoothness part. And now what is the square distance to the optimum? Well, in the worst case, let's say, you know, we start from like x0 being, you know, just like some, you know, like very silly. Let's say, actually, let's just think like x0 is 0. It's not exactly a unit flow, but like that's not a problem. Then essentially, in the worst case, we know that the optimum solution might have a 1 unit of flow on every edge. Okay, so in the worst case, this might be, you know, this might be as bad as m, right? Because every edge essentially will like, this is a L2 norm squared, so essentially every edge will contribute 1 to it. So we will get like theta of m, which, you know, we are in the sparse graph, so this will be theta of n, sparse graphs. Okay, so the total running time okay, sorry. Will be, you know, epsilon approximate solution in time O of essentially m epsilon squared. This is number of iterations times the time needed to execute a step. Time needed to execute a step is just exactly applying a projection, like gradient descendant projection. So this is near linear time. So for sparse graphs, this is this is O tilde of n squared over epsilon squared. Okay, so we just got a quadratic algorithm for approximate maximum flow. Yes.
So you're saying alpha and beta using epsilon.
So no, there is no alpha. So this is just what I said. Like essentially, there is like this thing is not strong convex for any alpha. Okay, and essentially what you do. So one way to derive this bound. So if there is no alpha strong convexity, just a convexity without any alpha, you can still get this bound of this in general. Okay, and then applying to max flow with beta being 1 over epsilon and this initial distance being m, you get the algorithm. So by the way, how to go around the fact when you don't have how to get some alpha? What you do is something called regularization. Essentially, what you do, you can take new function, which is your old function, plus a quadratic term. Okay, add it to it. This is the regularization term. So essentially, well, because of this alpha, like this is essentially in the Hessian, this will be an identity matrix. So this essentially will make sure that you have alpha alpha strong convexity. Of course, the price of this is that now the minimizer of your function changes. Okay, but like if you set alpha to be roughly epsilon over the initial distance, okay, then actually you will get strong convexity, and the error in your minimum will be just of order of epsilon. So just from our analysis, you will actually get you will get the right convergence. Like you will exactly get the bound over here. Okay, but yeah, but this is a bit too fast. So any questions? Yes.
Does this analysis go through if you assume approximate projections as opposed to exact?
Sorry, approximate
Projections.
Yes, but this becomes a bit. But yes, that's what Ludwig is doing, right? So Ludwig Schmidt. So yeah, well, so essentially yes, there is a yes. So actually, the answer is yes. Okay, so in general, like for convex set, this is known that is yes, and actually we will use it later on. that approximate projection is enough. It's even true for non-convex set, but then that's what Ludwig is doing. Then you have to be careful. Any other questions?
Can you remind why we use the infinite norm instead of L1 norm, please?
Oh, that's a great question. Yeah. So that's a great question. So L1 norm, so if you consider this problem, minimize x that belongs to f st of L1 norm of the vector. So this would correspond to a different graph problem. Do you see what is the graph problem here? Fedor?
Just not both ages, no?
No?
I mean, to pick only going out of S.
Yeah, no, because like you have this, so this is the right answer. So essentially what this corresponds to, this is the shortest path. Problem. Why? Because essentially what you are now doing, you have your graph S and T, and you know that like, because of these constraints, it has to be like, essentially you cannot just like, put edges here and then like essentially they have to be valid flows. So essentially you have to choose a way of sending one unit of flow from, from S to T. And what you want to do is you want to minimize L1 norms. So essentially well, it's not hard to see that essentially in the worst case, you can assume that you just use one path. And what you want to minimize is just you want to minimize the length of this path. Because that's what L1 norm is.
I meant that we just to norm, we take only the edges coming out or
No. The norm.
X as Y can do.
No. The norm is always well, X is.
We may take such function to optimize just a natural function for.
I see what you're saying. So you are saying that you want to formulate it like as as just essentially you look at the flow going outside, but that will cheat, right? Because imagine you have a graph looks like that. Okay, even on such a graph, if this is your S and this is your T, well, essentially, okay, I see you are. No, like first of all, like notice that here you set the flow from S, net flow from S to be always 1. Here you set the net flow from S to be always 1. So essentially, you know that if you look at the L1 norm of the things coming out, they will always be 1. There will be no differentiation between different things. So again, let's talk about this offline. But like just the point that I want to make is that, yeah, if you put here in infinity, you have max flow. If you put here 1, you have shortest path. If you put here 2, you have electrical flows. So there is actually very nice, this is the one formulation that gives you all these problems as you vary the norm that you are using. And this is actually quite fundamental, and it's too early for us to talk about it, but there is a reason why these things are like essentially like because of this is the case, we can this is the reason why we can use electrical flows to solve max flow. This is also the reason why we can use electrical flows to solve shortest path. Okay, and that's also what is possible to do. And essentially, in the end, all that matters is essentially how much the L2 norm is approximating L1 norm or L infinity norm. Okay, any other questions? Okay, so yeah, so just, it's still, as always, you think that, I think I was rushing a bit. I think I covered almost everything I wanted to cover, but yeah, I think it was a bit rushed. So I think you didn't ask enough questions. Yeah, next time I'm planning to actually apply these techniques to a concrete problem, which is not max flow, but like solving linear systems. Like I want to give you a glimpse of how to solve Laplacian systems. And hopefully, as we again see how this machinery is applied, it will be a bit more clear what's happened. But in the meantime, if there are things that you think were unclear here and you would like to go over them again, then tell me or tell Sasha if you want to anonymize your input. And I'm happy to essentially just redo some of the stuff next time. I also I can publish the notes from today, so you can just go over them and hopefully things become a bit more clear. What exactly happened. And again, it's just, I'm sure it's confusing at first. Again, for me it was for sure, but there's actually some reason behind this madness, and but you have to work it out. Like in the end, just looking at me going through this derivation will not be the same as if you actually go through them and try to do it. Okay, thanks.